Figure below shows a reversible cycle through which one mole of a monoatomic gas, ideal gas, is taken. Calculate A. The efficiencies of the cycle. B. The efficiencies of a Carnot engine operating between the highest and lowest temperature that occurs in the cycle. The value for the P0 and the V0 is given. So now in this diagram, three states are labels: state A, state B, state C. To find the efficiencies of the cycle from the A to the B, from the B to the C, and then back to A, we use this formula: eta equal to output work divided by the QH, where the QH is the heat absorbed by the gas. Output work is the work done by the gas. Eta is the efficiencies of the cycle. We can find the output work by calculating the enclosed surface area of this triangle. So it is equal to half of this length multiplied by this length. So this length, the value is 2P0 minus P0. And this length is the 2V0 minus V0. Okay, so we have half times the P0. 2P0 minus P0 is P0. And then this one will give us the V0. So this is the output work. Next step is to calculate what is the QH. Now there are three processes in this complete cycle. The first, second, and the third. From AB is the first, from BC we consider it as a second, and from the CA is considered the third. So now we need to know for these three processes, thermodynamic processes, which one the heat is absorbed by the gas and which one the heat is released by the gas. Only those processes where the heat is absorbed by the gas is considered as a QH. To judge which one is a QH, it is good if we can know what is the temperature for these three states, A, B, and C. To know the temperature, we apply the equation of state. From the equation of state we have, or the ideal gas law, we have T equal to PV over NR. But the N is 1 mole, which is a fixed value. R is a gas constant, also is a fixed value. That means the temperature T is directly proportional to the products of the pressure and the volumes. So now if we look at these three states, for the state A, the products of the PV is the P0 times the V0. For the state B, it is 2 P0 V0. And for the C, the products of the PV is a 2 P0 multiplied by 2 V0. So that means it is a 4 P0 V0. So that means if we compare the magnitude of these three products of the PV, we know that for the state A, the value is the smallest. And the state C is the largest, which is a 4 P0 V0. For A is only P0 V0. And the second, or the middle value between this state A and state C is for the state B, which is the 2 P0 V0. Therefore, we know that the temperature for the state A is the smallest, followed by state B, and the largest temperature is the state C. Now we can easily check which process the Q or the heat is absorbed by the gas, and in which process the heat is released by the gas. So for the process from state A to state B, this is the isochoric process because the volume is constant. So QAB is equal to NCV delta T. N is the number of mole and CV is a specific molar specific heat for the gas at constant volume. And this is the change of the temperature, and we already checked that this temperature for the state B is the larger than the state A. So that means this delta T is positive value. That means everything is positive value at the right hand side. The QAB should be larger than 0. So that means in this process, the heat will flow to the gas. The gas will absorb the heat. From state B to state C, this is the isobaric process. The pressure is constant at 2P0. So that means the heat, we can calculate the heat QBC by using this formula, which is the NCP delta T BC, where the CP is the molar specific heat for the gas at the constant pressure. We know this value of CV and the CP for the monatomic gas. Again, by checking the change of this temperature when the state change from B to C, we know that the temperature for the state C is larger than the state B. So again, that means this delta T also is a positive value, and QBC should be larger than 0. So in this process, also the heat is transferred to the gas, or the gas is absorbing the heat. In the last process, thermodynamic process for the entire cyclic process, that means it is from state C to state A, we can apply the first law of thermodynamics to determine whether the Q, the heat is transferred to or from the gas. Because this one is the compression process, the gas is compressed, so the work done, which can be obtained from the area under graph, should be the negative value because of the gas compressions. And because the temperature of TA is less than the temperature of the TC at the state C, that means when the gas evolve from the state C to the A, the temperature is dropped. That means the internal energy change in this process also would be a negative value. So based on the first law of thermodynamics, work done negative, internal energy negative, that means the heat transfer from the C, when the process happen from the C to A, should be transfer from the gas. So that means the gas is losing the heat. So QCA should be negative value. So now we know that for this cyclic process, when the state change from A to B, the gas absorb the heat. And when the gas change the state from B to C, also it will absorb the heat. So that means the QH composed of two terms, which is the QAB and QBC. For the process of from C to A, the heat is removed from the gas, so it is not part of the QH. So that means to evaluate the efficiencies of this cycle, to find the QH, we need to find out what is the QAB and what is the QBC, and we sum them up, we will get the QH. As mentioned before, process from A to B is the isochoric process. So QAB can be written as NCV delta T AB, and from the B to C, this is isobaric, Then we have the NCP delta TBC in the second terms. For monatomic gas, ideal gas, the CV value is 302R and the CP value is 502R. And the temperature change that happens between the state A and B can be calculated by using the ideal gas law, where the T equal to PV over NR. But now this change of the temperature is due to the change of this P products of the PV that happens between the state A to state B. So we have delta PV for this process from A to B divided by NR. Same thing happens for this process BC. So we have this delta PV BC over NR. The NR and the NR cancel out. In the second terms also the same. NR and NR cancel out. So that means in the first term we have 3 over 2. And this change of the PV, products of the PV, we look at this diagram, we will know. For the B, the product is a 2 P naught V naught, and for the A, it is P naught V naught. So that means the change should be equal to P naught V naught. That means 2 P naught V naught minus P naught V naught, you get 1 P naught V naught. And for the second terms, which is involved the B to C, the C, the products of the PV for the C is 2 P naught times the 2 V naught. And for the state B, it is the 2 P naught times the V naught. So that means this delta PV for the process BC is equal to the 4 P naught V naught minus the 2 P naught V naught. So we have 2 P naught V naught. After cancel out this NR, then it remains 5 over 2 times 2 P naught V naught. But the 2 and this 2 cancel out. So that means we have 5 P naught V naught. That means now we have this QH equal to 3 over 2 P naught V naught plus 5 P naught V naught. Then we get 13 over 2 P naught V naught. This is a QH. So now we already have the output work and the QH. Output work is half P naught V naught and the QH is 13 over 2 P naught V naught. So that means these two terms, these two quantities, both are expressed in terms of P naught V naught. So P naught V naught can be cancelled out, and then we will have 1 over 13. This is the efficiencies of the cycle. For the part B, we need to calculate the efficiencies of a Carnot engine operating between the highest and lowest temperatures that occur in the cycle. So the formula to calculate the Carnot efficiencies is 1 minus Tc over Th, where the Tc is the temperature for the cold reservoir and the Th is the temperature for the hot reservoir. From the result of the analysis that we performed just now, we know that in this entire process, the highest temperature is attained when the state is at C, and then the lowest temperature should be at A. So that means we substitute the cold temperature as the TA and the hot temperature as the TC to calculate the Carnot efficiency. Again, now we substitute the TA as the PAVA over NR and the TC as the PCVC over NR. We already applied these formulas, or we already have the experience of substituting the T in terms of these expressions just now, which is obtained from the ideal gas law. We can cancel out the NR and NR. So now we have 1 minus PAVA over the PCVC. Refer to the graph again. The products of the PV for the state A is the P naught V naught. So that is why we have P naught V naught here. And for the state C, it is the 2 P naught times the 2 V naught. So we have 4 P naught V naught. Cancel out the P naught V naught P naught V naught. Then second terms we have 1 over 4. So 1 minus 1 over 4, we obtain 3 over 4. This is the Carnot efficiency. Now we already have the answer for the part A and the part B. But what is the meanings of these two answers? It means that if there's a practical engine that using the monoatomic ideal gas as a working substance, the highest temperature that I can achieve in this practical engine is a TC and this is a TA. The efficiency for this practical engine is 1 over 13. But if there is a Carnot engine operating at the same highest and the lowest temperature, we can see that the efficiency is 3 over 4. So that means one is a practical engine, another one is the Carnot engine, both operating at the same highest and the lowest temperature. The efficiencies of the Carnot engine, which is the idealized engine, is far more larger compared to the efficiencies of this practical engine. The last noteworthy point is that although these questions give us the value of the P naught and the V naught, but in our discussions or the solutions, we never use these two value, simply because in our calculations to find out the eta and eta Carnot, all the P naught and V naughts are cancelled.